wants you to estimate Z of 9358, isn't it? So you're given a Z of TH table is given. So now, and this is what you want. You want to know approximately what this is, to the best of your ability. You're not going to get it exactly, but you can do the best you can. So how do you go about how do we do that? We did a problem like that out of the book. How would we do this one? We did something very similar to this problem in the book. So what would we do?
You take the partial of x and y. Oh, well, in this example, would be t and h.
Again, imagine you have this surface, but I don't know what it is, and I want the tangent plane. So I want to somehow, I know what maybe this is, I know what that is, but I want to estimate this, from here somewhere. I want to estimate this thing. So I'm going to need the tangent plane and estimate the surface value. So how am I going to get the tangent plane at, where would you want the tangent plane to be intersecting? Because I only have this table to work with, so where would you want it to estimate?
Didn't we use level curves or something like that?
Well, not really. Look, where would the closest point on the table be to where I want?
94 and 50 or 60?
Yeah, 9460. So I want to. So I know what Z of 9460 is, right? I have this point. So I want to estimate this, Z of 9358, which is off a little bit here. You see, so there's an error. There's going to be an error in the estimate from the surface that I don't know, and the value that I'm going to get, assuming it's flat. So I'm assuming it's flat in the neighborhood of this point. Right? So how do you do that? Yeah. What was that? How do we do a local linearization? How did we do such a thing? Well, go back to the original. What's a tangent plane? How do I get a tangent plane to something? What was the formula for a tangent plane?
Z minus Z naught. Can we use that?
Right. Normal dot r equals 0. That was the equation. So what was the point normal form?
Z minus Z naught equals, or x minus x naught.
Okay. Well, in this case, what would it be? Using these letters.
Still got to go at Z2.
X minus
There's no x's here, so
T or S of T or Z of T.
t minus.
okay. So what should I write here?
T minus 93.
What is this r vector? Just give me that.
Is it 0, 0, 1?
T minus some T naught, right?
Right. And
Right.
H minus H.
And then Z minus Z naught, right? It wasn't that the effectively, because you have this point right here is like a T naught, H naught, Z naught, isn't it? The point that we have is the point T naught, and then we want a point T somewhere over here, THZ somewhere over here. So this would be the point. So where is this T naught here?
That would be 94.
That's the 94, isn't it? And the H naught the Z naught. What is the value of this? Of the,
111?
of these. What was 111?
Yes.
111. So this would be 111. Okay. So that's a vector in the plane, isn't it? T minus 94, H minus 60, Z minus 111 is a point in the plane. All right, so what is the N? How did we, generally speaking, the normal vector was like minus, remember it was like, it was the alternate form, the standard normal vector was like minus Z sub what? Z sub X, but in this case, T and then minus Z sub H, comma,
Just negative Z, or was it just Z?
1. Wasn't it like minus ZX, minus ZY, 1? Does that sound familiar? Remember that stuff?
Mm.
So this is minus ZT, minus ZH, 1. And then this dot product will give you the local linearization model. So therefore, minus this partial of Z with respect to T times T minus 94, right? Minus this partial of Z with respect to H times this H minus 60 plus this Z minus 111 is equal to 0, isn't it? And so what is the local linearization model then? What did we solve for to get the local linearization model?
For Z.
Solve for Z, didn't we? Okay, because that's what we're looking for. We're looking for this Z over here for this particular situation. So the Z, which was the local linearization model of the TH, right, is equal to this is 111, let's see, plus, we could write it as Z sub T if we wanted to, I guess, times T minus 94, plus C sub H times H minus 60. So we could write it like this. And then we want, what do we want? L of what? L of, and we want this, don't we?
Yeah.
So this would be, we want L of, well, let's leave it this way. So we want L of 9358, which would be, what's this T here? Oh, 93 minus 94 plus 58 minus 60. Well, what does this come down to finding now?
Change the X and Y.
Well, we need
I mean,
Z
T
sub
and H.
T and Z sub H, don't we? But how are we gonna get that from this table?
2 point.
What would we actually want Z sub T at where? At,
93.50.
well, no, we want it at 9460, because we don't have it anywhere else, do we? We want this, and then we want this at 9460. We want these differential, derivatives at this point. That's the closest point to the point of interest. So, but you're gonna have to estimate this. So how are you gonna, we don't know it exactly, so we're gonna have to estimate it. How are you gonna estimate it? What's constant when you do this? H is held constant, and here, the T is held constant. So how would we get a derivative, an estimate of a derivative at 9460 with H constant? So the T is changing, the temperature is changing, but the H is held constant at 60. So what would be a way to get an estimate of that derivative?
Take Just change for each value over what the value of one. You wanna know?
Okay, what would it be on the left side? If you held 60 constant, what would the derivative at 9460 be estimated at? On the left, below 94. It's just a difference quotient. Just give me the difference quotient.
The 11 over 4?
11 over 4? Where'd you get the 4? Well, I agree with 11, but where'd you get the 4?
The 4 degrees.
Oh, yeah, yes. Yeah, I was looking at something. You're right. What he did was 111 minus 100 over 94 minus 90. Isn't that right? It's just a change in the temperature over the, I'm sorry, it's a change in Z over the change in the temperature, right? Now that's on the left side, right? But that's not necessarily the best estimate. So now look on the right side. What would the right side's derivative be?
12 over 4?
12 over 123 minus 111 over 98 minus 94. But these two derivatives, one on the left and one on the right, should be what? What should you do to these?
Divide by 2.
You should average these, right? So that would be the average temperature. That's the best estimate you could possibly get for this with this table. All right, so let's see, how much is that going to be? Somebody give me a number for that.
23 over 8.
Is that right? 11 and 12 is 23 over 4, 23 over 8. Yes. This would be 23 over 8. So that was the estimate, the best we can do for that. All right, do the same thing for this. But now the T is constant, isn't it? So now what would you get? Over, again, you're going to take an average again. You're going to take a couple of difference quotients. So,
7 over 10.
yes, 111 minus 104 now. On the left side, over 60 minus 50, right? And then the right side,
7 over 10.
also 7 over 10. 118 minus 111 over 70 minus 60. So how much is this? This is 7 and 7.
7 over
14 over 10 is 7 over 10, right?
So then divide by 2, right? Wouldn't it be 7 over 20?
I'm sorry, yes. Thank you. This was 7 over 10 plus 7 over 10 is 14 over 10. No. 7 over 10 plus 7 over 10 is 14 over 10.
Yeah, you're right.
Over 2 is 7 over 10.
Right.
Right? Or 14 over 20, yes. either one. Okay, so that would be, whatever that number is, would be your answer. How much is that approximately? 111 plus, actually 111 minus 23/8 minus 1.4 is whatever that is. Minus 1.4. Looks like you get 106.7. $106.7. So that would be, does that sound reasonable? Look at the table. Does that look like a reasonable number? Are you comfortable with that answer? Well, the temperature index at 9460 is 111 degrees, but you are a degree lower and 2% less humidity, so you're about 4 degrees less than the 111. That seems reasonable, doesn't it? I think that's, again, if we were way off, if we got a number larger than 111, or maybe if we got an answer of 93 or something, that would have been ridiculous, right? And you would have noticed that. But this number